Hello, everybody. Today, I would like to talk to you about some research that I've been doing looking at RNA mass spectrometry, and specifically looking at using more advanced software tools to deconvolute top-down RNA mass spectrometry. For those of you that might not be aware, mass spectrometry offers an attractive way for us to take a look at RNA and DNA when we're interested in more than just the primary sequence identity. There are lots of chemical modifications that occur that are relevant, and there is more and more interest in them. So mass spectrometry allows us to take a look at the mass of each specific base as part of an ion, and then from that figure out what the identity of that is. And my background was developing the nucleic acid search engine tool during my PhD, which is a component of the OpenMS framework. And this is a search engine that allows you to put in sequences, modifications that you're interested in, as well as mass spectrometry data, and provides you with information about where those are in your experiments and more information about them. So as a little bit of background, we've recently moved from looking at RNA and DNA in a bottom-up manner, that is to say, where it's digested down by enzymes to begin with and then reassembled in silico, to looking at it from a top-down perspective, which is where we give the entire RNA or DNA to the instrument, and then we try to figure out the ions, every specific ion along the length of it, and identify the sequence for it. And so this is challenging both analytically and computationally, and have been working on trying to improve the computational side of this. One of the challenges that we face is that the charge states on a lot of the longer portions of the ions are very high, and we would like to be able to figure out what the mass is, the uncharged mass, because despite the name, mass spectrometer only takes a look at the mass to charge. And so we need to be able to figure out the charge and then take a look at the uncharged version of it. And so this is called deconvolution, and this is important. And we are able to do that because the samples are inevitably going to have different isotopes attached to them. And so instead of having just a single peak, you end up with a couple of different peaks of different abundances that are separated by 1 over the charge state, because each of those represents an extra heavy atom. And we can computationally go through and deconvolute that to come up with the total mass. So here we've done this with the internal tool in the nucleic acid search engine, which is something that I presented on at American Society of Mass Spectrometry earlier this summer, as well as with a much more advanced tool, FLASHDeconv, developed in our lab. Qian Zhang was the main proponent of that. And what we wanted to see was whether using a more advanced deconvolution algorithm would improve our sequence coverage, so the number of ions that we were able to see, and improve the number of peaks that we were able to define out of our deconvoluted spectrum. And so as we can see here, we're looking at the comparison of the peaks. FLASHDeconv works a lot better. This is not especially surprising. It's a much more advanced piece of software. It takes into account a lot more about the isotope abundance and different charge states and whatnot. And especially as we look more toward the higher mass to charge ratios, we end up with many more peaks that show up with the FLASHDeconv rather than the internal naive model. So the second part then is, how does this affect the coverage? So does this improve our sequence coverage, and what does that tell us about the analytes that we're interested in? And we did this looking at a couple of different things, some tRNAs, so that's full length would be, I think, 70, 74, 75, and also a 100-mer DNA that we used sort of as a proxy for guide RNAs, which are something that are very much of interest right now in pharmaceuticals. And we found that this is the coverage plot where each bar represents a possible ion. The color represents the type. There are a couple of different types of ions that you can get with fragmentation. And we see really good coverage when we don't decharge. When we do decharge, we lose a lot of that coverage. And we initially thought that that was not necessarily a good thing. However, in review, we found that, first off, the peaks that we got out looked a lot better. The assignments were much more qualitatively good looking. We also were able to recapitulate the expected ion intensity preference toward the ends with our fragmentation type, and the ion type preference for, in this case, the A-B and W ions in the DNA. But we also would see the equivalent in the RNA of A and W ions. So this gives us more confidence, at least in the peaks that we are able to see. And we also found that, again, as one would expect from taking a look at the deconvoluted spectrum up here, that FLASHDeconv produced better coverage. It produced significantly higher intensity of all of the peaks. And it was able to help us recover some more peaks toward the center, so higher mass peaks. It also maintained the preferences that we saw for the expected ion types. So that's a quick sampling of what we've done. And this is really just sort of a step forward in figuring out how to do this top-down mass spectrometry, because inevitably we would like to be able to get back our coverage toward the middle. And I think that's going to take some analytical work, and I think it's going to take better methods for dealing with the noisy data that is higher charged. We're also going to work on figuring out quantitatively rather than just qualitatively the quality of the peak assignments that we get. This is a challenge because there's not really a good ground truth that we've established so far. So this is continued work in progress. And I would welcome if anyone has any questions, please feel free to drop me a chat. My email address is sam@samwein.com. Or I think there's also one attached to my profile. So thank you guys so much for your time and hope you enjoyed it. Bye-bye.